Yeah,
Yeah.
I've got a signal like that.
Yeah.
Okay, so we'll start.
Okay, sure.
Yeah, good morning all.
Good morning.
Yeah, today's lecture is about performance of digital modulation in mobile radio channels. And then, hold on. Okay, so we will, this lecture is going to dwell on materials from last year class, TE3H2, and then what we are doing currently, that is T8472. In TE3H2, we look at methods of what, or types of digital modulation. So in this class, what we're going to do is we're going to focus on two principal types. That is phase shift keying and then QAM. So when we deal with third year material, our focus will be on PSK and then QAM. Okay. Then when we come to this year, the mobile and satellite course, what we've been doing so far is to characterize the mobile channel. What does that mean? It means that what are the possible mobile environments can you have?
Yeah.
From our previous study, we have a non-fading, that is additive white Gaussian noise channel. We have flat fading channel. We have frequency selective fading channel. And then we have slow and fast fading channels, which we call time selective fading channels. So we have two things, the modulation techniques on one side, and then the possible channels on one side. So what our goal here is to study the effect or the performance of digital modulations in the various mobile channel. Is that okay? Is the introduction okay?
Yes, sir.
Okay, okay. Now, so this slide is just a review of the third year work. We have different types of modulation scheme. Like I said, Fig 1, in Fig 1, we're going to focus on PSK and QAM, okay?
Okay, sure.
Then this slide, when you come to final year, this is what we've been doing so far. We characterize the channel. We have the following: additive white Gaussian noise. Why do we call it non-fading? We'll see again ahead, but the meaning of this is that the signal during transmission from the transmitter to the channel is assumed not to be affected. That the effect on the signal is only at the receiver side. That is, at the receiver side, the noise is added to the signal. We'll see a model of this as we move on, okay? So that is what we call additive white Gaussian noise. Then the remaining, we have the flat fading, the frequency and time selective fading. So principally, we're going to deal with three channel situations. One, the additive white Gaussian noise channel. Two, flat fading. Three, the frequency and time selective fading channel. So these are the channels that we want to do. Okay, now, what is the framework? How do we want to study this? We want to study this in this framework. That is, from a typical communication point of view, we have the sender side, the transmitter side. We have data to send, but this data need to be transformed into signal, because the channel can only transmit signals. So what we're going to do in one framework, we're going to transform the bits, zeros and ones, into what we call the MPSK. That is, we are going to use phase shift keying, and then in the middle of the two, that's the transmitter and receiver, we can model the channel as any of the following four. Okay, that is, do we assume that the channel between the transmitter and the receiver is additive white Gaussian noise? Are we assuming that it's flat fading? are we assuming that it is frequency or time selective fading? If we assume any of these, then we do analysis on the received signal and see the number of the amount of error that has been made, and then we will be able to characterize the performance. So this is one framework.
Okay.
The second framework is what happens if we change the zeros and ones using QAM. Okay, we'll change the zeros and ones using QAM, and then again, in between the two channel, in between the two transmitter and then the receiver, that would model the channel as additive white Gaussian noise, flat fading, frequency selective, or time selective. So that is principally what we want to do. Okay. Now,
Okay,
the question is, how are we going to, any questions so far?
Yes, sir, please. With respect to the first framework that we discussed.
Okay. Mm-hmm.
The previous slide. Can you go to the previous slide?
Yeah. That's MPSK?
Yeah, that one.
Okay, okay.
Can you take the explanation again? Because it looks like I didn't get it.
No, the explanation for the MPSK is the same as for the QAM. What I mean is that we have zeros and ones to send. That's what we studied in data communication. But because these zeros and ones cannot be sent through the channel, we need to move them up into a carrier. That's the modulation part. So the technique of moving this from zeros and ones into a signal, we will going to use PSK, that's the modulation scheme that we'll use in converting the zeros and one to signal, will be phase shift keying.
Okay.
Is that okay?
Yes, sir.
So now that we have a signal at the transmitter, this signal needs to be moved from the transmitter to the receiver. The question is, what is the situation in between the two? Is the situation just addition of noise at the receiver? That is additive white Gaussian noise channel. Or we're going to say that there is some fading. That is, we have multipath in between the two. There will be some fading. You get it?
Yes, sir.
So we have two things. The signal at the transmitter, the channel will impose some conditions in the channel, whether it is additive white Gaussian noise or flat fading or frequency or time selective fading. Is it okay?
Yes, please.
Yeah, okay. So this next one is the same concept, but now we are using a different modulation scheme. So we will use QAM instead of PSK. The essence of this is we want to see whether the PSK or the QAM, which of them performs better. That's why we are using two.
Okay, sure.
Okay?
Yes, sir.
Okay. So if we looking at the framework, then how do we do the performance evaluation? The performance evaluation, we will use metrics. In our analysis, we'll use what? Two metrics. One, probability of error, that is bit error detection. And then we will use probability of outage. Okay, so these are the two normal metrics that are used in assessing any modulation technique in a wireless or mobile channel. The bit error rate, and then which we will normally call the BER, and then the probability of outage. Okay.
Okay, sure.
Any question on that slide?
No, please.
Okay. Now, what we're going to do is, if you have a situation like this and you want to evaluate the performance, you need some tools to do that. Let's say, for instance, going back to the framework, you have your signal at the transmitter side. You model the channel as either of the one of the three. Then you send a signal, it is received, demodulated, and then you want to see whether it is 0 or 1. Now, how do you do that? You can do that through analytical method or through simulation. Okay. When we say analytical method, it means that we can get some equations to represent the process. And then when we say simulation, it means that you need some simulation tool, either MATLAB or any other simulation tool to mimic the process, and then you collect information and analyze. So in this performance evaluation, we will use what? You can use two methods, that is analytical techniques and simulation. But in this lecture, since it is an undergraduate course, introductory course, we will try to explain the analytical part of it.
Okay, sure.
Is it okay?
Yes, sir.
Is it clear?
Yes, please.
Okay. So if you have additive white Gaussian noise channel and you want to use the matrix BER, that's bit error rate, it easily blends forward. It gives itself an analytical means of doing it. You can get equations when you want to get BER for additive white Gaussian noise channel. When it is flat fading channels, you can also analyze it using analytical. If you are using BER, dealing with probability of outage is a little bit complex, and then dealing with frequency and time selective environment is also complex. This you can only do using simulation. Did you get a difference between the two?
Yes, sir.
Yeah, so in BER, simple BER analysis in additive white Gaussian noise, we have a technique of deriving equations, and then we can do bit error rate analysis. We can do the evaluation. When it comes to flat fading channel, you can still do BER analytical analysis. But when it comes to BER and probability of outage evaluations, for frequency and time selective, the only way is simulation. Okay.
Okay, sure.
Yeah. So we'll take the additive white Gaussian noise, which we want to use as an undergraduate example to get an equation for, and then draw conclusion. All this, the conclusion is how does a particular modulation technique performs in a particular channel. That's all that we want to do. That's the trick in it. So now we'll take that additive white Gaussian noise channel and do a little bit of analysis on it, and see how we can get the equation. We are not going to do the derivation. We'll get the equation and then use some samples from literature to explain how it works. Okay, so if you look at this the slide, equation 1, you see that at the receiver side, the signal received is RT, the signal sent is ST, and then all that is added is noise at the receiver side. So this is a very simple channel. The signal itself between transmitter and receiver, it's assumed that nothing happened to it. And the only thing that happens is that at the receiver side, noise, NT, is added to it. So that is the meaning of this channel. And then what again we need to know is that the noise is constant, it's not changing. So this is a noise floor that is added to the signal. So if you have this type of things to do, then the analysis, the question to ask is, what is the signal part compared to the noise part? What is the signal? You receive a signal. All that you need to do is, what is the signal part of it, the power of the signal compared to the power of the noise? This gives us a metric called signal to noise ratio. Signal to noise ratio. So in the additive white Gaussian noise channel, all that we're interested in is you send a signal. At the receiver side, we assume a constant noise is added to it. And then we analyze it, and this is what we have. You have to measure the signal power, the noise power, the ratio will tell you the quality of the signal. Is this understood?
Okay, sure. But so I have
any question on this slide?
Yeah, a question.
Okay.
Okay, so my question is, when we are considering the AWGN channel,
Yes.
additive wide Gaussian noise, we are assuming that are we assuming from the transmitter to the receiver, nothing happens to the signal we are transmitting?
Yes, that's why it is the simplest channel you can ever have. The signal that is ST is assumed that it is the way it is sent from the transmitter. The only change it has is at the receiver side. That is, at the receiver side, noise is added to it. It's like a signal is sent from you from one classroom, and then we are in telecom 4 classroom, and then the signal came perfectly, but there's so much noise in telecom 4 classroom that you have to find a way of making sense of the signal that came in. So from 209 to 208, the signal came all right, but within the 208 classroom itself, telecom 4 students are making so much noise that that noise is now affecting the signal. That is the meaning of what? That is it clear? Equation 1. That's the meaning of equation 1.
Okay, yeah, it's fine.
So as we move on, you see that in fading channel, something will be added to the ST before it comes to what? The receiver. You get it? So take notice of equation 1. When we get to fading channel, you see that the ST, something will be added to it. And then that is why the DSP class you are taking is important. What is added to it is something that we'll talk about when we come to the fading class. Is this additive wide Gaussian noise channel concept okay?
Yes, sir.
Okay. So now that we have the signal to noise ratio, that we have a signal, it has come to the receiver, it has some power level. We studied in class that this power level we can compute. We have done a lot of examples to determine the power. So if you look at the equation, S and R is PR over N naught B. So you can calculate the power level and then divide it by the noise that is added at the receiver. So this is a metric that we'll be using. So what we need to do is the signal to noise ratio per bit is of importance to us. The signal to noise ratio per bit is of importance to us. The signal to noise ratio per symbol is also of importance to us.
Okay.
So if you look at equation 2 and 3, we need to go back to third year, TE3H2, to understand why we are dealing with bit and then symbol, okay? So if you look at it, equation 2 deals with bit, equation 3 deals with what? Symbol. The reason being that if you have some number of what bits to send, you can represent the bits with symbol. So for instance, if you have a binary scheme, 1 bit, you need what? 1 signal to carry it. If you have 4 bits, if you want to carry 2 bits at a time, then you need what? You need 2 symbols to do that. So if you have number of bits, you need some number of what? Symbols to carry it. For instance, if you have 8 PSK, you have 1 symbol. That 1 symbol is going to carry what? 3 bits for you. If you have 16 PSK, you have 4 bits to carry at a time. These 4 bits, 1 signal will carry it for you. So what you need to understand is when 1 signal is in fault, how many bits are affected? It depends on what? The type of binary, either you are using binary, you are using 8 PSK, you are using 16 PSK. So you need a relationship between the bits and then the symbol. Any question on 2 and 3?
No, sir. It's clear.
Is it very clear?
Yes, sir.
So in all the analysis we're going to do, we have to specify things in what? Bits, and then work out things in what? Symbol. And then you need equations for the mapping. So if you want to see at the receiver side, what is the ratio of the power in a bit to the noise, then equation 2 comes in. If you want to look at what is the energy of one bit with respect to in a symbol with respect to noise, then equation 3 comes in. So we need an interplay between bits and symbol because of what? The mapping that we need to do. Okay.
Oh, okay.
Okay. So this mapping, as we saw in TE382, this mapping you can do very well using signal constellation concept. Okay, so you need signal constellation concept. Most often in wireless communication, the bit error probability as a function of what? The EB over N naught is what we want to find out. Okay, our focus is what is the bit error rate with respect to what? The power or the energy in one bit with respect to that noise. So if you look at it, if you draw any graph, you have the bit error rate on the vertical axis, and then we'll have the gamma B or the gamma B on the vertical side. That's what we're going to do. Always it is what? What is this SNR per bit? That is gamma B. And then what is the bit error rate? So if you vary the SNR per bit with time, if you vary it on the vertical axis, what is the corresponding behavior of the what? Of the error rate? That is what we need to look at.
Okay.
Any question for me?
So yeah, there's a question.
Okay. Mm-hmm.
I want to get the concept of I'm seeing whether the concept of constellation diagram I have is correct.
Okay.
So I'm picking that it's a diagram that's made up of like two axes, which measures the symbol per bit, and then the SNR per bit, and then the SNR per symbol.
No. That's not the concept of symbol rate. That is the concept of what? Performance. You get it? I'm explaining two things here. If you look at it, the performance evaluation, what we need to do is you, at the transmitter side, okay?
Yeah.
You have a signal, you modulated it with a PSK, it has some energy in it, you send it to the receiver side. At the receiver side, you receive the signal, you measure the bit of it, the energy of it, energy per bit of it, and then you want to find out whether an error occurred or not. So in terms of performance, what we want to see is if you increase the SNR per bit, what is the effect on what? On the bit error rate. For you to be able to do this, then you need a signal constellation concept. As for that one, it is just a drawing that represents what? That represents the symbols. So as you can see on this particular slide, we have a PSK. This is what? 8 PSK. Can you see it?
Yes, sir.
So this drawing is what we call the constellation diagram. It is showing the symbols. The symbol is a dot, and then a dot of that dot is carrying how many bits? It's carrying 3 bits. Okay? So now when you send the signal using, for instance, in this case, 8 PSK, if you received a signal and it falls into, for instance, the red point that you have, then it means it can be detected to be 001. You get it?
Okay.
But if you don't get it well, then it means an error occurred. Okay? So what we want to see is what is the distance between the points. The distance between the points will determine the probability of error. If the distance between the points are too close, then when you receive a point, you can't tell whether it is in this quadrant or that quadrant or that portion of it. So this signal cancellation diagram, what it does is that it gives you a map or a drawing of the symbols and then the number of bits that the symbol carries. Any question on this?
Okay, sure. There's no question. It's clear.
It's clear.
Yeah.
Okay. So now you can see that we need a mapping from what? Gamma B when you have information on gamma S. So equation 4 does that for you. And then equation what? 5 does a conversion from what? PS, probability of a symbol error, and then PB is probability of bit error. Again, these two conversions are happening because of what? We want to carry what? We want to send bits, but we are transmitting symbols.
Okay.
We want to send bits. It is bits that we want to send, but the nature of the channel, we cannot carry bits. We can only carry symbols. So we need to have equation between them. So if a question is posed to you, the question will be posed in terms of what? What is the bit error or the gamma B will be given to you? But in your calculation, the information you get first will be the PS. And then you have to use the PS to convert into what? PB. So we have question 4 and 5 doing the mapping for you. Any question on this slide?
Yeah, the parameter, you see the formulas, equation 4 and equation 5, they have a common log 2m, but what can you explain the m value?
Yeah, the log 2m, it means it's just like the number of levels and then the number of bits you can carry. If the level is what? If the level is 8, it means you can carry how many bits?
3.
3. If the level is 4, you can carry what? 2 bits.
2 bits.
So the M here is telling you, based on the type of memory you are dealing with, if it is 16 PSK, then your M becomes what? 16.
Okay.
Then you will be able to determine that.
Okay.
Is it okay?
Yeah, it's clear.
So the log 2M tells you whether you are dealing with a binary, 8 PSK, 16 PSK, 32 PSK, or you are dealing with what? 4 QAM, 8 QAM, 16 QAM or not. So based on the type of modulation scheme you are using, then you can convert from what? Symbol to bit in terms of what? SNR per bit. Then you can convert from what? Probability per symbol to probability per bit. But in practice, what is needed is probability per bit. Are we okay?
Yeah, yes, sir.
Okay, so now when we say analytical, it means that we can derive equations. We can derive equations for whatever process we're doing. So we are saying that when it comes to additive white Gaussian noise, and you want to do BER evaluation, then we can do analytical method. The analytical method we can do using the cancellation diagram. So here, if you look at equation 6 is giving you the probability of what? Bit error. The probability of bit error. And then once you are able to determine the D minimum in that equation, you should be able to what? Get whether it is, if it is 8 PSK, the D minimum will change. If it is binary, the D minimum will change. If it is 32 PSK, the D minimum will change. So it depends on the type of modulation scheme you have. This D minimum will change. And based on that, we will come to what? Equation 7 and then equation 8.
Okay.
Can you get a relationship between equation 6, 7, and 8?
Yes, sir.
So all that we need is that if it is what BPSK, we can determine the what the D minimum. If it is MPSK, we can determine what the D minimum. The determination of the D minimum comes from the constellation diagram, which is not the subject of this class. So what we do is we're going to use these equations, especially equation 8, and then work with.
Okay.
Are we on the same page?
Yes, please.
If you look at equation 8, you see that for the MPSK, the equation is specified in terms of what? PS. That is, you are not directly given an equation for PB. But most problems, you will be asked to determine PB. That is why you need what? This movement. That's equation 5.
Yeah.
Do you get it?
Yes, sir.
Yeah, so you need equation 5 to always deal with stuff when you are doing BER. So the equation PS is given to you, that's the symbol error 8, rate, that is equation 8. And then from that, you have to convert to what? PB.
Okay.
Is this okay?
Yeah.
Very okay?
Yeah, it's correct. It's okay.
Okay. So now the question is, this equation 8 is what you have to learn how to use. If you want to have an analytical understanding of any signal, for instance, PSK in additive white Gaussian noise, then we need to deal with what? Equation 7 and 8. Okay?
Okay.
We're going to deal with equation 7 and 8. So if you look at equation 7, you see that there is a factor EB over N naught. Can you see that?
Yes, sir.
So the question is, if EB over N naught is increasing, how does it affect PB? That is what we will see shortly in what? A graph. If you are increasing the power, the signal power, that is EB over N naught, what will be the effect on the probability of bit error? That is equation 7. Equation 8, if you look at it, we have gamma S, gamma subscript S.
Yeah.
So that is what? A factor. If you are increasing gamma S, what will be the effect on PS? So it is the effect with respect to what? Gamma S or gamma B that we will use to draw conclusion. So at the end of this class, what we'll be doing is that we're going to draw conclusion. If you send a signal, a PSK signal through additive white Gaussian noise with increasing gamma B, what is the effect?
Okay.
If you send PSK signal through a flat fading channel with increasing gamma B, what is the effect? If you send a PSK or MPSK QAM signal through a channel with increasing gamma B, what is the effect? That is what we want to look at. Those are the conclusions that we want to draw in this introductory class.
Okay.
Am I clear?
Yes, please.
Very clear?
Yeah.
So at this point, all that you need is to solve an example using equation 8. Okay? Now, equation 9 is the same as equation 8. What you need to understand is that the angle should be in what? Degrees. Okay? In this equation, the angle is supposed to be in degrees. That is, anytime you are working with this, your pi must be what? 180 degrees. And then the equation 10 is what we're going to use to toggle between symbol and bits. Symbol and bits. Why? as I continue saying it is because we want to send bits, but we are what? Transmitting symbols.
Okay, yeah.
Is that okay?
Yes, sir.
Very okay?
Yeah,
okay.
All clear.
Okay, so this is a problem for you. We're supposed to compare the probability of bit error for 8 PSK and 16 PSK, assuming gamma B to be equals to that. In this analytical case, we are only picking one gamma B, but in analysis, as you see shortly in a graph, what you see is that gamma B will be what? Varying. You get it? So
Okay.
this particular case, I want you to use equation 9, and then what? For a particular gamma B, convert what? Calculate PS, that's probability of symbol error, and then convert to get probability of what? Bit error.
Bit error.
Yeah. So our interest is probability of bit error. You can only get there through what? Probability of symbol error. That's the message I want to send. Is that message clear?
Yes, sir.
Okay. So this is the equation for you. The first one is a relationship between gamma S and then gamma B. Because we know in the problem gamma B is given, but the equation we have is PS. So we need to first of all convert gamma B into that, okay? And then the gamma B that was given was in dB. In this equation, we don't deal with, we are not going to deal with dB, so we convert it. That's why we have 10, 15 over that. So it's a conversion from dB to non-dB. That gives us 10 to the power 15 over that.
Yeah.
Okay?
Yeah.
That's what you need to know. Then we invoke equation what? 9, and then that's what you have. If you do the substitution, that's the value you get. Now, this is what? Probability of symbol error, but we need probability of what? Bit error. So we do the conversion, and that is what we have. So you see the two values. So for 8 PSK, that is the value for what? Bit error rate at a particular word, SNR per bit, which is 15 dB.
Yeah.
You get it?
Yes, sir.
Okay. So at a particular gamma B, the bit error rate is what? 3.86 to the power negative what? 8. That's a bit error rate. So the question you ask yourself is, what is the interpretation of that? What is the meaning of 3.86 times 10 to the power 18? So you give me interpretation of that. What is your interpretation of that?
So I would say for the technique we are using, the 8 PSK, right? The probability of value has been, that's what we've calculated for.
Yes.
Yeah. So,
but I want you to put meaning on this for me. The meaning of PB equals to 3.86 times 10 negative 8. What does that mean?
It means that let's say a fixed energy per bit that we have.
That's 15 dB.
Yeah, that's the 15 dB. The minimum distance or the minimum error we can find per bit is 3.86 times 10 to the power minus 8.
Yeah, but what I want you to is to give me the explanation in terms of if you send how many billions or what number of bits, how many bits will you send before you get one error? That is the way you do explanation with this type of bit error. Do you get it?
Okay.
Do you get me?
Okay.
Yeah. So if you send 3.86 times what? 10 to the power 8, those number of what? Bits, then one of them will be what? Will be in error.
Be in error.
Yes. So 1 over this value, if you send that number of what? If you send that number of what bits, then you get one error.
Oh, yeah.
That's the interpretation you need to do. For instance, if we say bit error rate is 10⁻⁶, it means that when you send 1 million bits, there will be one error.
Yeah, yeah.
You get it?
Yes, sir.
When the bit error rate is 10⁻⁶, it means that when you send 1 million bits, one of them will be in error. That's the meaning of this.
Yeah.
Is that okay?
Yes, sir.
Okay. Thanks. So in the same manner, we do 16 PSK, and then you look at the value. So all that you need to do is to compare the bit error rate at what? The bit error rate at 8 PSK and 16 PSK. What is your comment about the two values?
Okay, so comparing the bit error probability for the 8 PSK and the 16 PSK, we can see that the probability for error is very bigger or is very large for the 16 PSK.
Okay.
And then we've also discussed that because that's the answer we are expecting. We are expecting that the 16 PSK will have a higher than the 8 PSK, because we said from the constellation diagram that for the 16 PSK that we have,
that's correct.
We have more bits per symbol for a given constellation diagram.
And then they'll be closely packed.
The minimum distance will be small, so that means they are closely packed. Yeah.
You got it.
Yeah.
You got it. Yeah. Okay. There we go. So this is PSK. Okay. So that is PSK for you. Then the MQAM. The MQAM, again, we have equation 11 to deal with. Okay. So all these things were derived, and then we have PS. So if you want to have a more exact way of calculating MQAM, then you use equation 11. If you want to approximate it, then you use equation what? 12. So equation 11 is exact form of what? MQAM. And then equation 12 is an approximated form of what? For MQAM. Is that okay?
Yes, sir.
So again, what we want to see is, if it is a curve, if it is a graph that we are drawing, we're going to vary gamma S. If we vary gamma S, what will be the effect on PS? That is the conclusion that we'll be drawing shortly. Is that okay?
Yes, sir.
So when it comes to the MQAM, we have two equations. Let's say, for instance, you have 16 QAM. You can either use equation 11 or equation 12.
Okay, sure.
Equation 11 is an exact method, and equation 12 is an approximate one. That's all that you need to know about this QAM stuff. Is it okay?
Yes, sir.
Okay. So, for instance, if you want to repeat the question we have on the other side, then you can go through this question. Okay. Then we will use the exact method, that is equation 13. Look at the value. Okay. Then we will use the approximate, that is equation 14. Can you see that?
Yeah.
So you see that in terms of 13, and then with respect to 13 and 14, the variation is not that much. That's all that this problem want to prove to you, that you can use approximate, which is easier to handle, and then the error will not be that much, 7.37 and then 9.82.
Yeah.
Can you see that?
Yes, sir.
Okay. So that is what you have. But the interest is, look at the figure of what? The value of what? 16 quam. I'm going back. 16 quam. What do we have? We have 4.8375 times 10 negative 4.
Yeah.
That's 16 quam. Is that okay?
That's 16 quam. Okay. Yeah.
That's correct. No, that's 16 PSK.
Yeah.
That's 16 PSK. So now, this is what we have for 16 quam. 16 quam, we have what? If you use the approximate, it's 9.8. If you use the exact, it is what? 7.36. What is your comparison between 16 PSK and 16 quam? You understand the question I'm asking?
Yeah, I get it.
Yeah, okay, go ahead.
In terms of the value appearance, I would say I would say the 16, for 16 quam, we have the value to be a little bit greater, like 4 times or 3 times approximately greater.
Don't forget the negative, we are using negative. So is it greater or less?
So for the 16 PSK that we have, the value is, let's say, 4 times larger, or let's say 3 times, or 3 to 4 times larger than the PSKs, the 16 quam.
The 16 quam, okay. Yeah. So the practical conclusion from this is that in wireless or mobile communication, most often 16 PSK is not used. Do you get it? Okay. With this comparison, anytime you are using, you need an application, you need a data rate, and you work up to 8 PSK. If you need to go toward 16 PSK, then the alternative choice is to move toward quam. Okay. Does it make sense?
Yes, sir.
Yeah. So up to 8 PSK, the PSK and the quam, they perform almost okay. But as soon as you move to 16 PSK, the quam performs way better than what? The PSK. So in practice, what you need to do is that when you're dealing with any application that requires data rates that 8 PSK cannot handle, then you move to what? Quam.
Okay.
Is that okay?
Yeah.
Okay. So that is it about the analytical part with respect to what? Additive white Gaussian noise. Any question on that?
No, we can continue.
Okay. So this is what we were talking about. This graph, that's figure 4. Figure 4, it is the analytical and then simulated. If you use the equation we have in equation 7 or so, and then you vary gamma B, this is what you have. Do you get it? Okay. As the SNR per bit increases, you see that the bit error rate decreases. We have the bit error rate on the vertical side. You see that it is decreasing as SNR per bit increases.
Yeah.
Can you see the curve?
Yeah.
So on this slide, whether it is theoretical, that's analytical, or simulated, it doesn't matter. The nature of the curve is what we need to focus on. The nature of the curve is what we need to focus on. What is the type of curve what is the type of curve in front of us in Fig 4?
Is it a waterfall curve?
Okay, but mathematically, what do we call this?
Hello, I don't get it. I don't get that question.
Is this linear, exponential, inverse? What is this? How does this look like?
Hello? Yeah, I don't get a question.
Yeah, can you hear me?
Yeah, I can hear you, but I don't get a question.
I'm asking that if you look at this curve, is it linear? Is it inverse?
No.
Is it exponential?
It's decreasing exponentially.
Thank you very much. So in our conclusion, these are the terms that we want to do. If you look at this curve and all the curves for additive white Gaussian noise, when you increase the SNR per bit, you see that irrespective of the type of PSK you have, all of them, the curve, the decrease in BER is exponential.
Oh yeah.
You get it?
Yeah.
So this is a conclusion we want to draw. That is, in additive white Gaussian noise channel, if you increase SNR per bit, the bit error rate decreases exponentially.
Okay, yeah, yeah.
Can you see that?
Yeah.
So irrespective of 8 PSK, 16 PSK, 32 PSK, we can see that all of them decreases exponentially, okay? Although 8 PSK is better than 16 PSK, is better than 32 PSK. But the conclusion, the import of this graph is that increase in SNR per bit reduces the bit error rate exponentially.
Okay, yeah.
Is that okay?
Yeah.
So this is what we can say from that. Now, in terms of practical application, if you can reduce something exponentially when you increase SNR per bit, it means that you can use transmit power. You can use the transmit power to reduce what? The bit error rate.
Yeah.
Do you get it? Do you get the implication?
Yeah.
You increase SNR per bit error rate falls exponentially. It means that it is economical, or at this point in additive white Gaussian noise channels, you can use the transmit power to reduce what? Error. Do you get it?
Yes, sir.
So that's the conclusion on the additive white Gaussian noise channel. Okay?
Yeah.
Whether in QAM or that. So that is what we have. Is that okay?
Yeah. Doc, I have a question.
Go ahead.
Okay. So what we are saying is that for the technique we've studied right now, we increase, when you say when we increase from the graphs, when we increase the power to noise ratio,
The SNR per bit.
the SNR per bit, yeah, we decrease the error exponentially, which is good for us. But what you are saying also is this the SNR per bit can be achieved by increasing the transmit power.
Yes.
Yeah. And so my question is, so with that, because we want to so for an instance where we want to achieve very, very small error, it means we have to or we have to transmit at a very high power, right?
That's the import of it.
That's the implication.
Yeah, that's the implication. That is, okay. If it is additive white Gaussian noise and you as engineer in charge, you recommend that they should use transmit power to reduce bit error rate, you will not be killed.
Okay.
You get it? Because you will not make too much, the cost will not be too much.
Okay.
You get it?
Yes, sir.
So now we are going to fading.
Okay.
You get it? So in fading, we want to see whether that same technique can be used.
Okay, sure.
That same transmit power, can transmit power be used to reduce the bit error rate? If it can, technically, is it business-wise okay? That is the cost.
Okay.
Do you get it? Then we go to frequency selective, and then time selective and see whether transmit power can in any way reduce the bit error rate at all.
Okay.
Do you get where we are going?
Yes, sir.
Yo. So we have 3 mobile characterizations. 1, additive white Gaussian noise. We have flat fading. We have frequency and time selective. Now we've done everything on additive white Gaussian noise. We made a conclusion that because when you increase the transmit power, the bit error rate decreases exponentially. It is okay to do that up to some point. But we are now going into flat fading and see whether that can be done. And if it can be done technically, what cost will it be to us? Then from there, we move on to frequency selective and then time selective environment and see whether the transmit power needs to can be used. Why are we doing this? If you look at the projects that we have, we are making a case that in mobile environment, based on additive white Gaussian noise, flat fading, frequency selective, you may need to call on some other techniques to reduce bit error rate.
Yeah.
Do you get it?
Okay, yeah.
So the default way of reducing bit error rate is what? Increasing the transmit power.
Yeah.
Do you get it? And so all that we want to do is, can you do that in a fading environment? Do you get it?
Yeah.
That's what we want to those are the conclusions that we want to draw.
Okay.
Is that okay?
Yeah, that's fine.
Okay. So for instance, in the white Gaussian, additive white Gaussian noise, what we noticed was that the noise that is added is constant, okay? But if you come to a multi-path environment, shadowing environment, in class, we said those things result into what? Random variables. Things become random, okay?
Yeah.
So when you begin to come to an environment when random is coming in, then we need to talk about what? Probability, density, and stuff like that. Do you get it?
Yeah.
And then again, BER may not be the best method of what? Of evaluating the performance. So that is why we bring in probability of outage too, okay? But
Yeah.
as an undergraduate class, we will not touch the probability of outage analysis because of the work involved in it. That's why we are just focusing on the BER.
Okay.
Are you with me?
Yes, sir.
Are you with me?
Yeah.
Okay. So this is what we have. In a fading channel, if you look at equation 16, at the receiver side, we have RT as the signal. Then from the transmitter side to the receiver side along the line, there is something in there. HT is added to the thing. There's some convolution. Do you get it?
Yeah.
And then the noise. So this is the difference between additive white Gaussian noise and then fading channels. So additive white Gaussian noise gives you the simplest, but it is not realistic.
Okay.
You get it?
Yeah.
It is not what exactly or what actually happens in a mobile channel. So it is not a good representative of mobile radio channels. No. So if you use additive white Gaussian noise, for instance, somebody is working on wireless sensor networks, he is doing thesis on it, and then he says he's assuming additive white Gaussian noise. As soon as the person opens his mouth and say that, then you can challenge him or her and say, no, that is not representative of what happened in a mobile or that channel. Do you get it? So
Yeah.
any work at all, your assumption must be solid. So anytime you assume additive white Gaussian noise channel, you are just saying that this is the class 1 of it. So it is not realistic at all.
Okay.
Did that make difference between equation 1 and 16?
Yes, sir.
So we can now move on with the fading. So this fading, we are saying that for BER evaluation, you can get a little bit of analytical representative of it, but the equations are so complex that as an undergraduate class, we will not do that. So when you have this, when you have equation 16 and you are dealing with it, depending on the path, the multi-paths that you have, depending on the multi-path that you have, we will have this type of what? Variation in the received power. The received power will be fluctuating, okay? That's figure 7. The received power will be fluctuating. It will not be what? Constant. So we need some probability to predict or to represent the variation of power or the amplitude in what? In an environment. So what we have is that we have mostly we have 3 methods of modeling fading channels, especially the multi-path ones. We have the relay channel, we have the Ricean, and then we have the Nakagami models. Okay?
Yes, sir.
When you have the multi-path channels that are contributing to the received signal, if they are so dense, if they are their density, the density of the multi-path channels determine which of the 3 you use. If you have a line of sight among the multi-paths, then you can use the Ricean distribution. If there's no line of sight, then you can either use Rayleigh or Nakagami.
Okay.
Any question for me?
Not yet. We can continue.
Good. So all that you need to do is to look at the multi-paths that you have at the receiver. You have a received signal. It is a contribution from multiple paths. What is the density of the path? If the density is so high, then the Nakagami is cool. Do you get it?
Okay,
if the density is not very high, but you don't have line of sight, then the Rayleigh is cool. If you have the density, but you have a line of sight signal among the received signal, then the Ricean is used. So these are the 3 distributions that you use in a fading channel. And then the analysis, we can't, undergraduate course, we can't. So all that we need to do is to look at the graphs. Do you get it? If you look at figure 8, if in a flat fading environment, you look at the PSK, DSK, and then FXK, can you describe the variation of that graph with respect to EB naught, that signal per bit?
Yeah.
You get a question?
Yeah,
okay.
I get it.
So in additive white Gaussian noise, you can see the curve, it is exponential.
Yeah.
That's why we concluded that transmit power can be used. Now, look at the flat fading one. That line, the 3 lines, how do they look like? What mathematical thing would you use to describe them?
It's a linear graph.
So that's inverse graph. You get it?
Inverse linear graph.
So it tells you that if you use transmit power to reduce bit error rate in a fading channel, you're going to need a lot of power to do that. It's not dropping exponentially, as you can see. Do you get it?
Yeah.
So that's the import of it. The import is that the meaning of it is that in a fading channel, flat fading channel, the decrease in bit error rate is inverse with respect to what? SNRP bit. It's not exponential. So at this point, it means that we have to begin to look for DSP techniques to reduce bit error rate. You get it?
Yes, sir.
So this is the reason why we are doing those projects where we have diversity, adaptive. We have other things that we're looking at. They are techniques that we will use in fading environment to reduce the bit error rate instead of using what? Instead of using transmit power. Is that okay?
Yes, sir.
Good, good, good. So again, all these graphs just to carry the same information, the import of it. So that's what you have. So now when you come to frequency selective and then time selective, this graph, you can see the graph after some value, the graph is not going down. It is flat.
Yeah.
Fig 11.
Yeah.
After some value, it is very flat. Because it is flat, we call it irreducible error flow. That is, you can put any power on it, it will not go down.
Okay, sure.
You get it?
Yes,
You can increase the transmit power to any value, it isn't going to go down. The bit error rate will not reduce. So we said that in frequency selective and mode channels or time selective channels, if you have that, then you are going to meet irreducible error flow, which you can only use what? DSP techniques to what? Reduce.
Yes, sir.
Did that make myself clear?
Yeah, it's clear.
It's clear, okay. So
Yeah.
all the rest, the remaining class, this is the same thing. For instance, you have frequency selective. If you don't use equalization, that is what you have. If it is flat fading, this is what you have. If it is non-fading, this is what you have. That's fig 12. Now, look at this. If you do some technique like equalization or so, then it will come down. That's the meaning of fig 13. Fig 13 is saying that if you apply any of the techniques, equalization, OFDM, that's multi-carrier, any other mitigation technique, then you should be able to reduce the BER. Are you with me?
Yes, sir.
Okay. So principally, the conclusion is that in flat fading, these are the techniques that you need. You need coding and interleaving. We need adaptive techniques. And then in frequency selective and then time, we need equalization, multi-carrier, spread spectrum, and antenna solutions. So in all, if it is an additive wide Gaussian noise channel, the likelihood of reducing bit error rate using transmit power is there at little bit of cost. If it is flat fading, the cost is high. If it is what? If it is frequency selective, transmit power will not, underline, will not be reduced if we send it to infinity. So it is just making a case that in mobile environment, we need to introduce some mitigation techniques. Thank you very much. Any question for me?
Okay, so let me ask a question with respect to the ISI channels and then the flat fading.
Okay.
Yeah. So ideally we saw that for the flat fading and then the ISI channel, we saw that we can't actually reduce the errors using the transmit power we can reduce the error by increasing transmit power, right?
No, flat fading you can, but it is not good because of the cost.
Okay, okay, sure.
Flat fading, it is linear. Because of the the inverse nature of it, the cost will be so high. Okay? But as for ISI, it will get to a point where we have that irreducible error flow. No amount of power will do it. That's the difference between them.
Okay, so that's what I wanted.
So additive white Gaussian noise, the reduction is by exponential. Flat fading, it is inversely. And then in frequency and time selective, we have irreducible error flow, it will not go down. That is it. So in flat fading and then frequency selective, time selective, it is always required that you do some DSP techniques to reduce the error rate.
Okay. Okay.
Okay. So thank you very much. Thank you.
Okay, sure. Thank you.
Thanks.